Capacitance. And so what I was going to explain in that last video is I was going to give you a conceptual reason for why for a parallel plate capacitor the capacitance is epsilon naught A over D. Okay, to do that I need to just show you how you charge up a capacitor. Okay, so if we have a parallel plate capacitor, let's have it look like this. Here's the parallel plate capacitor. These are two plates. These aren't wires. These are actually plates. They have some area to them. And then what we're going to do is we're going to connect them to a battery. Now, the way that we represent a battery, if you remember from last year, is we put that symbol. This represents the positive terminal of the battery, a DC battery, and this represents the negative terminal of the battery, or sometimes called ground sometimes. Okay, so here's your capacitor C, and there's your battery. It's got a certain amount of voltage. What's going to happen when you connect this is the electrons in this plate right here, they are going to see this positive charge, feel that positive charge, and they're going to zip over there to be with the positive charge. So if electrons leave this plate, that means this becomes positive. Electrons from here will go on to this plate. Now what will happen is that will continue to happen until there'll be so many electrons on here that these electrons here won't want to come over here anymore. I mean, this can get so crowded that it's going to start to push back so much that the electrons will just stay put. Same thing with this. The first few electrons will gladly go over there, but it's going to be tougher and tougher to coax electrons off of here because there's a lot of positive charge here. So if you're an electron moving that way, you're going to feel these positive charges pulling you back. So when will the charges stop moving? Well, when the voltage here is the same as the voltage there. That will happen in a nanosecond or even sooner, but it will happen very fast. But they'll stop charging when the voltage here is the same as the voltage there. In other words, when these are at the same potential, no more charge will flow. Okay. There's a rule that I'm not sure if you learned last year, but there's a rule called Kirchhoff's loop rule that says if you start any point in a circuit, doesn't matter where you start. Let's start here, and if you go around the circuit, doesn't matter which way you go around, but if you go around the circuit, that you have to gain as much voltage as you lose. And so if you go up a certain amount, let's say this is 2 volts, you go up 2 volts, and then you go around. When you drop this way, you're dropping volts because the electric field is this way, so you're actually going down in voltage. So if you go up 2 volts, you go down 2 volts. Okay, so you get 0 there. In other words, if I call that point A, and I say, what is the voltage at A with respect to A? Well, there can't be a potential difference at A with respect to A. It's 0. And so let me do a path integral. The path integral is going to go like this. Now, if this is all in equilibrium, in other words, the charges are done moving around, then in this metal has no field in it. There's no field in there. So when you do your path integral in the metal, you get 0 plus 0 plus 0. Now when you go across the battery terminal, you do get some voltage. So you gain some voltage, and then you don't gain any more. E dot dRs are 0. And when you get to here, you start to lose voltage. So you're actually dropping voltage. And then you come back around, and the only way this path integral can be 0, and it has to be 0 because the voltage at A with respect to A is 0, the only way this path integral can be 0 is if you gained as much voltage here as you dropped there. And so that's called Kirchhoff's loop rule. We'll talk more about that in a bit. So all that's saying is that the sum of all the voltages around the loop, the sum, that's a summation symbol, of all the voltages around the loop, any loop, is equal to 0. It's a very, very handy rule to have. Okay, well, what I wanted to do is I wanted to tell you why this formula makes sense conceptually. This formula is only used for parallel plates. And let me tell you why this makes sense. The A makes sense conceptually because the bigger the plates are, the easier it is to store charge. So think of a little plate. Think of this, if this one down here were just this little tiny plate, you'd put a little charge on there, and after putting just a smidge of charge on there, there'd be so much tension pushing the electrons the other way that no more electrons would be able to get on there. It'd be kind of like the first electrons would get there, they'd be like, hey, this place is really little, let's make sure none of the other electrons come on because we don't have any space in here. Whereas if this were a huge frontier, like a huge amount of space, then the electrons could come in and set up shop, and there would be no overcrowding for a long time. And so that would afford a lot more electrons on there. Okay, now why the D in the denominator? The D in the denominator is because when this gets charged, see these electrons here? They actually push the electrons from this top plate off. So these electrons are helping push the electrons off the top plate. And conversely, see these positive charges? They are actually helping this electron that doesn't know if it should come onto this plate. These positive charges are actually helping that electron be motivated to come onto this plate. Okay, so what happens when you make the distance smaller, if you make the distance really small, is these can help the electron get onto this plate more easily. And if these are much closer to this side, then they'll just push the electrons from here more easily away. So the smaller D is, the more these two plates can help each other get charged up. That's why D is on the bottom. See, if we make D small, the capacitance goes up.